Welcome to a discussion with Shuaiqi Wang and Giulia Fanti regarding Statistic Maximal Leakage. We're going to focus on this new privacy metric called Statistic Maximal Leakage and also some of the mechanisms associated with that. I hope you enjoy our discussion. It would be interesting to talk about the motivations for introducing a new kind of privacy metric. So we have the paper on the screen, the Statistic Maximal Leakage that you're introducing. Would you mind providing an overview of why there was the desire to introduce something like that to begin with?
Sure. So data sharing is becoming more and more important. For example, there are many regulations globally requiring data sharing with governments regarding the cybersecurity incidents, or for the enterprise space. One example is an automobile company that shares the data with a third-party vendor to design an autonomous driving system. So a major concern associated with those data sharing is privacy. And the organizations that share those data may want to share and collaborate, but they may not want to risk leaking those sensitive information, either about their users or about their internal trade secrets. So in the research community, we have spent a great deal of effort understanding how to protect those privacy of individuals for those shared datasets. For example, we have proposed a differential privacy. But we have paid less attention to the problem of leaking secrets from the dataset that can be inferred from the dataset as a whole. For example, the auto manufacturer may not want to reveal their vendor what fraction of their sales are sedans or SUVs. And these are global property of the dataset. So in our work, we aim to propose formal methods to measure the privacy of those global properties of the dataset.
Are
If I
there
may jump
currently...
in, sorry.
Yeah, sure.
If I may jump in briefly, I think we've talked to a number of companies that run into this problem. So they want to share data sets either internally or with third parties. And one of the big fears is, are we leaking our trade secrets? And these are often things that are properties of the entire data set, as Shuaiqi mentioned. And so understanding how to formally protect those kinds of functions of the entire data set is a relatively less studied problem.
Are there, in addition to that, adversarial attacks taking place on datasets like this? So the datasets that are currently protected, because I take it that we are proactively protecting datasets even right now, although we could enhance the space. Are there adversarial attacks currently being crafted as well to try and get through those defenses? Are you aware what the space looks like from that perspective?
Well, right now, from a practical standpoint, I would say the de facto mode of operation is to just not share data.
Mm-hmm.
So oftentimes these kinds of concerns preclude any kind of data sharing, which I think is damaging to the ecosystem as a whole.
Mm-hmm. Okay, very good. So how about we give a very high-level introduction of what the most common techniques for protecting data are, or rather, if we talk about protection metrics or privacy metrics, what the most common ones are, so that we can frame the discussion for the statistic maximal leakage.
Sure. So previous work on protecting those kind of trade secrets can be classified into basically three categories. So the first one is heuristic methods, such as not releasing some column of the data or subsetting the data. So those methods are commonly implemented in practice, but do not have any formal privacy guarantees. And another category is methods that based on a notion called indistinguishability. So let's do the following thought experiments, for example. Let's call the original data set we want to share as A, and we want to modify it in a way that hides the secret. And we call this modified dataset as B. So those indistinguishability-based methods add the noise to those released data, such that the observer cannot tell if the original dataset was A or B. And this guarantee should hold for any different pair of the datasets. So this is also the idea of the notion of differential privacy, which which focus on a different goal than protecting the global property of the dataset. So the main criticism of this method is that they may need to add a lot of noise to the data so that it may really hurt the quality of the released data. And the last category is approaches that adopt the information theoretic approaches to measure the leakage of information. So one important metric is called maximal leakage. Maximal leakage measures the leakage by computing how much the adversary's chance of guessing the secrets increases after seeing the released data. So most of those information theoretic leakage-based methods assume that the secret we want to protect is not known by us in advance. But in our work, we want to focus on those third settings, but we want to compute the leakage only for certain kind of secret.
Okay, so we will get to, I think, the parameterization of maximal leakage compared to statistic maximal leakage in a second, and then we can look at the specific differences between those. But I take it that on a conceptual level, the main reason or main motivation for introducing this metric to begin with is that we want something compatible with data sets where we actually know the secret that we want to protect. Is that understanding right, or am I getting that wrong?
Yeah, correct.
Okay, cool. So maybe we can talk a little bit about the data set itself, because there's a particular parameterization of this that has to do with the random variables representing both the secret and then also the data set itself. Would you mind describing why the data set is parameterized in the way it is? So we have this data set and it's parameterized by a random variable. And why do we have a setup akin to this?
Sure. So for the parameterization, because in practice, if we think about an attacker, they may also want to if they want to get some global property of the data set, which means they may want some summary statistics of this data set. And in this case, they may also want to parameterize it as based on some distribution parameter. For example, maybe some fraction can be parameterized based on some histograms, or if they want to measure some global properties, maybe they can use mean or variance or the quantiles of a distribution to represent those secrets. So that's a reason why we also want to parameterize those data sets and analyze the secrets, how to protect those secrets based on those parameters.
Maybe I can jump in as well here. So in general, I would say there's two different ways of trying to formalize the notion of a trade secret. One is to think of it as a function of a data set. And that's that's kind of what differential privacy is doing in their definition of their specific secret that differential privacy is hiding. The second way of formalizing the notion of a trade secret is to think of it as a function of some underlying distribution from which this data set is drawn. So for example, as Shuaiqi mentioned, maybe the secret that you're trying to hide is the 95th percentile of your sales, something like that. So in our case, we decided to model this problem by defining trade secrets as a function of the underlying data distribution for a couple of reasons. One is that it helped with the analytical tractability, but the other is that in some sense, we wanted it to be independent of whatever randomness happens in actually selecting the data set. Because typically what they're actually trying to hide is a property of some underlying process from which the data is drawn. So we thought that even from an operational standpoint, it made sense to define this secret as a function of the underlying distribution.
Okay, so I think I get the first part. We're saying that we're parameterizing the data set by means of a random variable because we're assuming that in an application of this, we would draw data from some underlying process that contains random noise in it, so that we're not necessarily modeling one static static data set.
Exactly.
Okay, and here comes my follow-up question then. So you also have a function that connects this data set to your secret, and the reason why the secret, G, I believe it's referred to in large G in this document, is also modeled as a random variable, and that's simply due to the fact that your original distribution of data is also modeled as a random variable? Or is there some additional reason why big G is also modeled with the help of a random variable?
No, your understanding is correct. Yeah, the reason it's random is because the distribution itself is random.
Okay, so then if we go to this part of the document here, we're saying that small g, which is a realization of this random variable, could be one of s different values. And the way to think about that is like akin to a time dimension, that you're saying you could model this data set across time, and then you would have slight variations in the data, and each time instance would then correspond to one instance of this random variable g, which can take s values.
Yes. Yes. We can. I think basically this is the potential value that we can the secrets can be, and in practice maybe this can be continuous. But if if we measure it, we can measure it based on certain precision, so that in this case we can due to the precision limitation, maybe we can also discretize it as several values, discrete values.
Yeah, again, this was a modeling choice. So for example, if the secret that we're trying to hide is the fraction of vehicles that a company sells that are sedans, we were thinking of this as a discretized set of numbers between 0 and 1, since it's a fraction. And we're saying, and we're representing that fraction up to a certain precision. So that's why we model this as a discrete set. In principle, this could also be a continuous set.
Mm-hmm. Yeah, that's part clear. And the last part I want to confirm is that the fact that it's being modeled as a random variable overall is then a carryover effect from the fact that we assume the data distribution to be random. There's the function that connects the secret to the data set is a deterministic function, right? And there's no additional point of randomness, let's say, in that sequence.
Correct.
Okay, very good. But then I have the background. Maybe we can then talk about these properties that are critical to privacy metrics that you raise in the paper and how they relate to some of the existing ones, particularly maximal leakage.
Sure. So basically, we have three desired property we want to achieve, and also as shown in this paper. The first is prior independence. This means that if we design a metric, we want our metric to be independent of the any parties prior of the original data. And this is because in practice, we cannot, it is very difficult for us to get the prior of the distribution. And even if we get this prior distribution, maybe there's also a mismatch. So it should be very impractical and also very difficult to measure if this metric is dependent with prior information. And the second is secret specific, which means that the data owner knows the secret in advance. So we assume this because in practice, if we share the data set, the owner knows what the sensitive information they do not want to release. And also, by assuming we know this secret, we potentially could also design mechanisms that achieve better utilities, because with certain secrets, we know more information we want to protect, so we can protect it more efficiently. And the other property is composition and post-processing. So those are also the properties that the differential privacy has. So basically, the composition means if we apply our privacy metrics, if we apply our mechanisms sequentially, so what happens to the privacy metrics? Does the privacy decrease linearly or exponentially? This can be characterized by the composition property. And for the post-processing, if we apply any, after releasing this data, if we apply arbitrary function, as long as this function does not depend on the original dataset, the privacy does not degrade. So this is also very important in practice because after sharing the data, the attackers or the data users can post-process this data with whatever functions they want. Yeah, and we want to ensure the privacy does not degrade.
If we talk about composition, for example, I would like to know in a bit more detail how that relates to the privacy metric as such. So we will talk about mechanisms. So for example, randomization in the output. And I take it that those mechanisms are not robust against repeated applications, which would then be highlighted, I suppose, by this composition property, but I'm not quite sure about that point. To me, it seems like this aspect of composition is not a design choice of the privacy metric itself, but more a design choice of a mechanism that you would apply in the pipeline. Would you mind elaborating on where my understanding there is lacking a little bit?
Sure. So the way how the privacy degrades may depends on what mechanism we apply. But this composition property here we want to analyze under the worst case. What is the worst case? So under any mechanisms, the privacy how the privacy degrades the lower bound of it under the worst case. So intuitively, if we release a dataset multiple times, they may intuitively release more information of this data. So how does the privacy decrease? Maybe it's universally, whatever the mechanism is, they may also have a pattern how the privacy degrades under the certain metrics. And what we want to do is analyze this kind of universal pattern of how the privacy degrades.
Mm-hmm.
And just to note, this is a similar type of guarantee as what is proved for differential privacy. So no matter what mechanism you're using, as long as a mechanism satisfies differential privacy, if you compose it sequentially, the resulting privacy guarantee of the composed mechanism will be at least this good.
Okay, thank you for the addition. Then maybe we could touch upon how maximal leakage also, like whether or not it satisfies these criteria. I take it that it satisfies some, right? But not all of the design principles.
Right. So first, it is not secret specific because the maximal leakage assumes that we do not know the secret we want to protect in advance. So in this case, they measure the privacy based on the worst case. So it's based on the secret that under which secret the information leaks the most, and they choose a secret to measure it. But in our case, we want to know the secret in advance. And this is the main difference. And also, they do not have a general analysis for the composition properties. Although they have some, under some certain cases, they have some composition property, but it is not a general analysis of it. And also the post-processing properties, they also may not have a very general analysis of it.
Mm-hmm. I want to look at the formulaic differences between statistic maximal leakage and maximal leakage in a second. But before that, I also want to touch upon the utility metric that I think you list in one of the introductory sections here. So particularly this equation right here. Would you mind describing what this utility metric actually tells us? What do we use it to, like, what do we evaluate with the help of this utility metric, and how does it work on a high level?
Sure. We measure the utility. We measure the utility by the distance, and here we use total variance distance. And this is distance more suitable for the tabular data which we analyze in this paper, and also we take the as we can see that before this distance we also have this expectation and this subterm. So expectation means that because for our mechanism, data release mechanism may have some noise, have some randomness, and we want to measure the expected utility over the randomness of this mechanism. And there is also a subterm before this expectation. And this means that because we do not want to depend on the prior of the distribution, so we take the worst case utility over all those data prior distribution.
Okay, so with this one, this one here, we're essentially saying, with the sub operation here, we're essentially saying that we're maximizing over all priors for the data distribution that we could potentially have.
Yes,
Okay.
that's right.
Okay, is this the only relevant utility metric that you could construct, or are there also competing alternatives to this one?
In this paper, we focus on these metrics, but you are right that they may also have different utility metrics. Even for the distance-based utilities, we can also adopt different distance, such as Wasserstein distance or even the KL divergence. And beyond the distance-based utility metric, we can also measure the downstream utilities, such as how good of the measuring how good the release dataset by training machine learning models to see the performance of these models. So this can but this is more specific to the application.
And
But more
how
gen-
come? Oh, sorry. Go ahead.
More generally, in the privacy literature, it's very common to try to analyze privacy utility trade-offs. And there's a lot of different types of utility metrics that people use, ranging from things like mutual information to maybe some kind of L2 distance, expected L2 distance between the released and the original statistic that you're trying to release. So in this case, this particular metric that we settled on was governed by some of our modeling assumptions, like the fact that we modeled the data as coming from some underlying distribution. That's why we have to have this supremum over distributions out front. And also the fact that our distance here is measured in terms of distances between distributions and total variation distance.
Mm-hmm. Okay. And is this one particularly suitable for tabular data? That's how I understood it before. First of all, if that's the case, and if it is the case, is there a concise reason why this particular metric, maybe putting aside the supremum for a moment, but just this this distance metric that we're using, particularly suitable for tabular data?
Right. So because for the tabular data, more specifically, for example, for the categorical data, so typically we measure the distance of those category data is if they are different, then we measure the distance as 1. If they are the same, the distance is 0. So this is also what the total variance distance works. So for example, we have tabular data, and some of them are categorical, some are discrete, and we calculate some if the element of each data is different, then we measure it as distance 1, otherwise it is 0.
To add on that, I think there's some other distance metrics like Wasserstein distance that have to be defined over a metric space. So that doesn't really apply in the case of tabular data.
Okay, very good. Then let's move on to some of the definitions here. So I want to look at the statistical maximal leakage definition that we have here in equation 1, and then also the maximal leakage definition down here. Now, looking at these, the only difference I was able to spot is in the supremum operation here on the left, and particularly what priors we're referencing here. Would you mind elaborating on what exactly the difference is between these two metrics in terms of how they're calculated?
Right, sure. Intuitively, that is the difference that ours is secret specific and theirs is secret agnostic. So, mathematically, in our case, because the only difference, as you mentioned, the supreme is over p theta. So, p theta means the prior distribution of the dataset. And in their case, the maximum leakage, the supreme over P of G given theta. So this is a secret function and so that they take the sup over all the secrets, which is more like they want to measure the privacy under the worst case secret function. But in our case, we want to measure the privacy given a secret, but we measure it given the worst case of the prior distribution. So this is also what we want. We want the prior independent.
Okay, maybe we can step through some of the details of this as well. So we have this expression here, log, and then P of G hat equals G, and then supremum in the denominator. Would you mind breaking down what we actually look at here? Like what are the metrics conceptually evaluating?
Sure. For the numerator, it is P of G hat given G. So intuitively, it means given the released data set, what's the probability that the attacker can guess the correct secret. And the denominator, it is just based on the prior distribution, and we take the supreme over this prior. So which intuitively it means that before release this data, if the attacker correctly knows the prior distribution, what the maximum probability they can correctly guess the secret. So we take the ratio of this guessing probability before and after releasing those data set. So intuitively, this ratio means the gain of the probability that the attacker can correctly guess a secret.
Okay. How come we're actually using the random variable large G here? So we referenced before the difference between an instance of this random variable and the random variable itself. Are we saying that someone external would need to be able to guess the entire random variable as opposed to just the particular instance that we're looking at now? Because I take it, again, that the randomness in this random variable comes from the fact that we're potentially reconstructing the data set over time, and that we might have variations in terms of how the data set is constructed. This to me looks like we're saying that the metric is concerned with someone being able to guess what the random variable will be irrespective of the, let's say, data acquisition process or something akin to that. I would have just naively expected that instead of large G, we would reference like the particular instance, so the small g. I might have gotten something there backwards, but would you mind elaborating a little bit on why why the large G is being referenced as opposed to the small g?
Sure. So here the small g means realization of a random variable, but here we want because we have the randomness of the underlying distribution. So with this randomness for the release data, they also have a randomness over if given the randomness of the original data. So the output should also have a randomness, and based on the attacker strategy, if they want to guess the secrets, so even if this attack strategy is a deterministic strategy, if there is a realization of the release dataset, for sure it can guess it deterministically. But here, we also have a randomness over all the original data, so that in this case, what the attacker gets in that view will also be a random variable.
Okay. Okay, so actually if you wanted to evaluate something like this, all the information that you would have at your disposal would be, if I'm not mistaken, like just the particular instances of the data set. So like one particular instance of the data set and consequently also one particular instance of the secret. But the underlying quality that's of interest here is whether or not the adversary or the counterparty is able to get the relationship correct. That seems to be the thing that we're actually trying to model with this metric. Did I understand that in the correct way?
That's right. And note that this privacy metric is a property of a mechanism and a secret. So that's, as you correctly pointed out, it's not specific to a single data set realization. It's looking over all possible priors and realizations of the data set, which is why it's written in this way.
Very good. That brings us nicely also to the mechanism. So let's talk briefly about those. I think there are two mechanisms being presented in the paper. Would you mind just elaborating a little bit on what those two are and how they work?
Sure. Here, those two mechanisms are not new, which also adopts in previous differential privacy literature or some other privacy literatures. The first one is called random right response. So this is a mechanism. Intuitively, it means that we release the true answer with a higher probability, but there is also another probability that we randomly output a random answer, answer. And for the quantization mechanism, intuitively, it means that we have several potential value of the secrets, and we divide those potential secrets into different bins. So if the realization of the secrets falls into a certain bin, then it will output a same value if the secrets is in the same bin.
So we're effectively, are we just effectively lowering the resolution in the quantization case? It kind of seems like it, at least that there's an aspect of lowering the resolution from a continuous variable or a continuous function to something like a more sawtooth kind of behavior. Or maybe sawtooth isn't right, but more like a plateauing behavior.
Yeah, right. So we can intuitively think about thinking like lower the resolution, and there's also a minor thing here is that because we only focus on how to hide the secret rather than how to hide the overall distribution. So even if we lower the resolution of this secret, but we still can have a very high utility or high resolution as a whole for the overall distribution.
Okay. Just a sort of tangential point to this, which is not really related to the paper, but just out of curiosity, when it comes to organizations publishing numbers with that are potentially sensitive, are they allowed to modify those numbers according to these kind of schemes, or are there, generally speaking, regulations that prevent that? Like these ones are promising alternatives, it seems, for hiding the particular information from a theoretical point of view. Does that also align with what can practically be done from the perspective of an organization, generally speaking?
I think that depends a lot on the use case. So for example, there have been cases of companies releasing traces from data centers where they were able to change these kinds of secret quantities. Or for example, they might remove the units, and so you don't know like the actual scale of the data that they've released. In other cases where you're trying to share data to, for example, comply with regulations, that I assume you could run into problems. But those kinds of questions are beyond my pay grade.
Right. Okay. Understood. Good. And these two, are these sort of the main approaches to doing this, or is it more specific to the particular use case that we had in mind now with this parameterized version of the dataset?
Yeah, so we define those mechanisms based on our mathematical formulations of the parameterization of the dataset. But we think those mechanisms can be suitable for either the tabular data or even for the continuous data set. It should be suitable.
Mhm. Okay. So maybe we can have a look then at some of the evaluations associated with this. So I think there are a couple of figures in the paper.
Mhm.
Maybe we can start with this one, because this is somehow a comparison between these two mechanisms. Would you mind describing what we're seeing in this figure?
Sure, sure. This figure basically it is a privacy utility trade-off analysis. So x-axis means privacy under our metric statistic maximal leakage, and for the y-axis it is a distortion, and it is based on the metric we have discussed before. So we compare it between those two mechanisms. The yellow curve is the randomized response. The blue dots shows the quantization mechanism. Here it is. I'm sorry.
Just a quick note. Here, lower statistical maximal leakage means stronger privacy. So 0 is like the lowest statistical maximal leakage you could have. That's the strongest privacy guarantee. And distortion, again, the lower, the better. So ideally, we want to be in the bottom left corner here. Sorry, Shuaiqi.
No problem. Yeah, yeah. Sure. In this, yes, as Julia mentioned, we want to achieve the left bottom corner. And here, for the quantization mechanism, it is we can see that in the almost all the cases, it is in the left bottom, more left bottom than the randomized response, indicating that it will consistently achieve better privacy utility trade-offs. So yeah, so in this case, we can see that for the randomized response, although it has been very commonly adopted in differential privacy or some other areas, but in our case, maybe it is not a perfect choice. We can simply lower the resolution, and this can achieve better performance.
Do you have a conceptual view on why there's a notable difference between these two approaches?
Um, Yes, so for the randomized response, it will output either its correct answer or other answers. And for if they output the other answers, it will output it uniformly at randomly. So, however, for those parameters that parameterize this data distribution, the support of this parameter should be very large, so that if we uniformly randomly output those parameters, maybe in most cases, this distribution parameter will be very far from the current parameter, and this will cause a very large distortion. But for the quantization mechanism, we quantize those distribution parameter, and for each bit, those distribution parameters are closer compared with the output of the randomized response. So the distortion will potentially be reduced.
And as a follow-up question, our metric for the statistic maximal leakage here, so the privacy metric, we're evaluating that, let's see, somehow more or less continuously in the distance, or we're using a distance metric that compares distributions for the random variable that we're hiding compared to the guess of the person evaluating this. I'm just trying to wrap my head around what the privacy metric here captures in this case, but we're saying effectively, if I understand this correctly, that we're able to protect the secret, and the way we do that is by ensuring that the guess in terms of distribution compared to the distribution of the random variable, that there's a large discrepancy between those, whilst not incurring a large overall discrepancy in the data. Is that understanding correct? Or maybe if you could elaborate on the distortion metric again a little bit, what exactly we're comparing it to. Because I take it that the random variable, we're comparing how large the distribution varies, but I'm not quite sure what we gather from the distortion side of things.
So for the distortion, it measures the distance based on the whole data distribution. So it is we use a distribution distance measure to measure this distortion. But for the privacy part, we only focus on the secrets. So it is not the whole distribution. It is just some function of this distribution. So we measure the probability gain of successfully guessing this secret rather than successfully guessing the overall distribution. So in this case, we can we can measure one part. For the privacy part, it is secret, the function of the distribution, and for the distribution distortion part, it is the distance between the overall, so the whole distribution.
Okay, thanks for the clarification. There's quite a few things we could discuss in the paper, and we're starting to get short on time. So I think the next thing I would like to discuss is I'll skip the computational aspect for now, and maybe we'll just focus on the second result graph. Would you mind giving an introduction to what we can see in this one?
Sure. In this one, we adopt a real world data set. I think it is a global income data set in the 1990s, and also it is also a tabular data, and we want to hide the proportion of the white and non-white high income people within their own race groups. So and here we adopt the quantization mechanisms with different privacy levels. And in this plot, we train several random forests to as downstream utilities, and to measure, and those plots shows the false positive and true positive rate the random forest perform. And we can see that for each curve, it corresponds to a different level of privacy. So the blue curves show the original data set, which means we do not use any data release mechanism. So the privacy is totally corrupted. And for those for those other curves, they will adopt the quantization mechanism with a privacy value from 0 to 2. So if the privacy value is 0, which means it can achieve perfect privacy. So the attacker can not have any information gain based on the released dataset. So this is shown in this red curve. And we can see that even for under this perfect privacy constraint, the AUC also do not drop a lot. It only drops around 0.14. So this is because what we want to protect is not the overall distribution, but some function of this distribution. So in this case, we can still have a high utility in this case, even if we protect some function of this distribution.
Do you have a view on how the choice of secret affects the shape of a graph like this? So we're saying that we're able to have perfect privacy in this particular instance without severely affecting the true positive rate of this random forest algorithm in the downstream. That to me seems to depend on how we choose our secret. You could choose a secret, as far as I've understood the paper so far, to be the entire data set if you wanted to. We have no restrictions on how we choose that random variable. do you have a view on how robust a graph like this is against your choice of secret?
Sure. So you are right that this may depend on how these secrets relate to the overall distribution. So in our case, the secrets only relates to two factors of this data set, the income and the race of this person. So it is not reflects the overall distribution. So it can we can see that it can achieve better performance. But if we if this secret is related to all the attributes of this person, uh, probably this may achieve may lead to a worse utility. Yeah, so it would also be interesting to analyze how the relationship between the secrets, the choice of secrets, and the job of the utility in this case.
I think one thing to note is that in our analysis, some of our analytical results hold only for a certain type of secret, which is the fraction of a category in a categorical random variable. And so that was primarily what we've evaluated empirically. However, you're absolutely right that different choices of secret could be much more correlated with your downstream task performance. And in that case, you should expect to see a bigger drop in performance. We don't have those results yet, but yeah, you're right.
Okay. Just as a follow-up question, if we go back to the previous figure as well, assuming that we don't have any kind of correlation between, well, the downstream system in the latter example, but we're just talking about sort of a generic situation where we have some secret in our data set, and it's maybe more of a question of how large, or quote unquote, how much data is included in that secret. Do you have a view on how robust, like, the performance of these mechanisms would be, like how the relative performance of these mechanisms would depend on that? Do we expect there to be across the board an enhanced performance for the quantization mechanism as opposed to the randomized response, or is that something where we expect it to be highly dependent on like each use case, so that we can infer something in this particular case, but not generally speaking?
So so if I understand correctly, you're asking, so with different type of secrets, how the performance of those two mechanisms performs, if there is a case that the random response will outperform quantization mechanism. So is this your question?
Yes. Yes.
Sure. So yes, so this is a very good question, I think. So it was further exploring. So I think this could happen, but intuitively, what makes the quantization mechanism superior is that it will have this quantization part. So this will group those parameters that have a closer distance, so that intuitively it will have better utility performance. Well, for the random response, because it outputs randomly all the potential distribution parameters. So in this case, the distortion will be unexpectedly high in this case. But you're right, if we assume, for example, in the extreme case, if we assume the secret is a distribution as a whole, so in this case, the random response and quantization mechanism will not have a very large performance gap in this case.
Mm-hmm. Yeah. Okay, but we're expecting, at least as a general note, that the quantization approach would be, generally speaking, better across the board. Would that be a fair statement?
Yeah, so yeah, the intuition is that.
Okay.
I think one other point that might be worth mentioning is that the quantization mechanism kind of notably does not satisfy a pure differential privacy guarantee, whereas randomized response does. So there could be other reasons not to use quantization mechanism. For example, if you want both a statistical maximal leakage guarantee and a differential privacy guarantee, that it might not be the right choice.
Mm-hmm. Perfect. I think that brings us to the conclusion of my questions, sort of very particular to the paper. I would turn it and look forward in terms of what follow-ups you think would be interesting to pursue as a consequence of this research, if there's anything that came to mind where you think perhaps additional research is needed, or applications that struck you during the process.
Sure. Yes, we have mentioned several during the discussion. For example, the analysis of how the choice of secrets will affect the final utility, or the analysis of the mechanisms. And also, as we think, maybe because in this work we assume there is only one sensitive secret, but in practice, maybe the company may care a lot of parts, and they may model the secrets as a multi-dimension vector. So in this case, whether our framework can generalize to this case, or we need to propose some add-ons to our frameworks. This is also directions that was exploring. And also here we focus on the tabular data set, but we may also, in practice, maybe we also need some continuous space and some other more complex data set pattern. So to evaluate our framework under those more complicated data set pattern will also be important.
Very good. Last question from my side. Sorry. Please go ahead.
And I think in addition to that, we would really like to try to understand try to bring it to organizations that are trying to share data and running into this problem, and get that kind of feedback on does this meet the kind of privacy needs of the organization? And this will run into some of the issues that you mentioned earlier.
Mm-hmm. Okay, very good. Then for the last question, I would just ask if there's, from the perspective of the wider research space, if there's anything that you think requires additional focus from other people working in the space that isn't properly addressed right now, and that you would sort of ask the wider research community for.
Sure. In my view, I think most of them focus on the privacy of for the individuals. Of course, this is a very important research topic, but in another level, we also need to pay at least equal attention, which is to protect some global property of the data set, because nowadays the data sharing is more and more important, and because for the large foundation models training, the current data may not be sufficient, and we need to generate more synthetic data or share more originally private data. So how to ensure that the company shares this data without release some business secrets should be a very important problem. And in my view, this problem is less studied and was exploring yeah.
Very good. Then from my perspective, I'm happy to close it here. Thank you both for taking the time to do the interview. I appreciate it a lot, and had fun going through it. So thank you.
Thank you so much.
Thanks so much for having us.